bong, 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 bong.
अरे यार
चल ठीक है. Okay, so let's quickly revise what we've done so far today. It wasn't much. We started with what's called motion of a rigid body. So we first need to define the concept of angular velocity for a rigid body. To do so, consider two frames. One is the fixed or inertial frame, which we label with x, y, z. The other one's called the moving frame, which we label with x1, x2, x3, or equivalently with small x, y, z. The position of a point on the body, we call it P. So we label it with different vectors. So with respect to the fixed origin inertial frame, we call the point P by small r. We call the origin O with capital R, and then we refer to the point P with respect to the origin O as cursive R. Okay, so that is the position of this point vector, or this position P, with respect to the moving frame, which is fixed to the body fixed frame. Okay, so now let us consider an infinitesimal arbitrary displacement of the rigid body. And when we do that, we can write it as dr. So this is how these vectors are related. So we already know that you can write small r as capital R plus this small r. But when you want to write the change in r, that will be given by a change in dr plus a rotation, which is the change in this small r, because it's a rigid body. So the only possible change in small r will be given by a rotation. And this we have actually already done last time. So this is d phi cross r, and that is because when you do a rotation, I can actually quickly show it to you. Or can I? Okay. So when you do a rotation, so this is what it looks like. So about the point O, the axis of rotation is represented by this line. If this is theta and you're rotating by an angle delta phi, then this change in r will be given by this r into whatever sine theta into delta phi. That is the length of delta r, and that you can neatly write as delta phi cross r, which also has the sine theta component in it along with the direction. So that's what we have here. Dr is equal to dr plus d phi cross r. And you can take the time derivative to obtain that the velocity small v is equal to capital V plus omega cross r, where omega is called the angular velocity. So this was angular velocity for, okay, so let's try to see why this omega has a good meaning for the whole body. Why that works is, well, let's start with assuming that we have another origin. So the body fixed coordinate is not actually at the center of mass, it's at O prime. Now in this frame, the point P will be given by R prime. The location of O prime is represented by R prime. This point anyway remains the same. So the coordinate of this point with respect to the fixed frame is still smaller. Okay, so now we observe that you can write small r as small r prime plus a, which is fine. R prime plus a gives you r. And now what you do is you substitute in your original relation, which was this. So in this relation, you substitute for small r. And what you obtain is that v is equal to capital V plus omega cross r prime plus a. Okay. Similarly, what one can do is using the same logic that we used here, you can write the expression for the primed coordinates. And in that case, you would get, and this remains v again, okay? That is because this r coordinate, the point P in the fixed frame is the same. So v is equal to v prime plus omega prime cross r prime. Okay. So now if you just compare it, assuming that omega prime and omega are the same, then if you compare the coefficients, you will get v prime is the same as v plus omega cross a, and omega cross r prime is equal to omega prime cross r prime. Okay, and we have okay, and apparently from this it is implied that omega is the same as omega prime. Okay, I don't think you have to assume this, so I'm not completely clear with how we derive this. But okay, so but the point is that the omega and omega prime being same basically tells us that the angular velocity of the rigid body is the same regardless of which frame you attach to the rigid body. Okay, and that is true for a given instant. So now, as all frames have the same velocity, angular velocity omega in direction and magnitude, therefore we can call omega as the angular velocity of the body and not about a point, because so far we'd only defined angular velocity of a point, not of a rigid body. Okay, so now we discuss something called the instantaneous axis of rotation. Again, I'm not super clear about it, but let's just quickly look at the few things I did understand. So V and omega are assumed to be instantaneously perpendicular. So V is the velocity of center of mass, omega is the angular velocity of the body. And if you make that assumption, then you can show that V prime dot omega prime will also be perpendicular, and that you do by just expanding it out and plugging in the expressions. Next thing you show is that you say that you can write, so you'll show that the velocity of all the points of the body are perpendicular to the angular velocity. That you do by just writing small v as the expression we had, v plus omega cross r, and when you do dot, you will see it's perpendicular. Okay, so now if you have v and omega perpendicular, then you can actually construct v prime to be such that, so remember, your v prime was v plus omega cross a. So you can always, if omega is perpendicular to v, then you can always find some a so that this expression disappears. Okay, and remember the fact that omega and v have to be perpendicular is important, because if they are perpendicular, then when you take a cross with omega, then the resultant vector will lie in the plane containing v. Otherwise, it will lie outside, and then you can never cancel it out. So that was one thing we did understand. So what that tells us is that you can always find some origin O prime such that your V prime is equal to 0. Okay, and since V prime is equal to 0, then motion through this point you can actually take to be pure rotation with the axis passing through this point. Okay, and yeah, so I think that's all that we did today, and we'll clarify a few things hopefully next time. And until then, as usual, if Kishore has something to say, we can listen to him. Kishore?
Thank you.
Okay, that's the standard reply, and so we'll see you next time. Thank you for not listening.
Okay.
Bye.